So last time we were talking about regularization and power counting. And in particular, we argued that there's some things that are nice about dimensional regularization when you're doing dimensional power counting, which is what we've been discussing so far, power counting in ratios of mass scales. So I want to continue along that theme today, and in particular move towards really talking about matching calculations in the context of massive particles. So just continuing with this discussion of dimensional regularization, we also have to pick a scheme. And the scheme that is a nice scheme for dimensional regularization is this MSbar scheme. There's some things that are good about it. Well, it's good because it works under the context of dimensional regularization and preserves, and it doesn't mess up any of the nice things about that regulator. So it preserves symmetries, gauge symmetry, Lorentz symmetry, the things we mentioned last time. In terms of doing calculations, it makes them technically easy or easier. So a lot of, if you look at like the literature and you look at multi-loop calculations, they're all done in the MSbar scheme. And there's a reason for that, because you haven't introduced these extra scales that would make your loop calculations more complicated. And finally, in the context of our discussion, of effective field theory, it's nice because it often gives what I would call manifest power counting, where we can power count both the regulated diagrams, the renormalized diagrams. We don't have to worry about whether we've added the counter terms or not. We can just do power counting. So if there's some good, there should be some bad. So what's the bad? Nothing is free in life. So one thing that we kind of lose with dimensional regularization is the physical picture. When we had this cutoff that we introduced, or if you have a Wilsonian picture, it's very clear what you're doing as far as removing degrees of freedom. And in MSbar, that's a little less clear. So if it's just less clear, but it's still fine, that would be, that would just be a technical aspect, and we would just pretty much ignore it. So I'll give you one example of something in which the picture being less clear could actually mislead you. So if you calculate some renormalized quantities in MSbar, you could have some a priori knowledge that these renormalized quantities should be positive. Maybe there's supposed to be a kinetic energy of some operator, higher dimension operator, that gives a kind of higher order kinetic energy term, some kind of physical intuition that it should be positive. Well, that might not be true in MSbar, because MSbar loses this physical picture. You're removing just the 1 over epsilons. You're not really having any control over the constants, or the constants are kind of predefined. If those constants are kind of too negative, then you can end up with renormalized matrix elements in MSbar that could be negative, even though your physical intuition tells you they should be positive. So that's something to be aware of. Where a physical picture could guide you and tell you what to expect, but you might lose that by using MSbar. There's another thing that's kind of technical, but is worth knowing, and we will talk about it a little bit more later. You could ask the question, is the Wilsonian picture and the Wilsonian scale separation really equivalent to the scale separation that you do in dimensional regularization? And the answer is almost, but not quite. It certainly is for all the log terms, and I mentioned last time that the log terms that we saw in the two ways of doing the calculation, you could just see a direct correspondence between them. But there is a leftover residual effect called renormalons that does show up in the MSbar scheme and is related to power divergences. And so this effect is carefully hidden. It's actually hidden in the asymptotics of the expansion in alpha S. And it goes under the rubric of something that people call renormalons. So there is a leftover physical effect from kind of having the freedom to drop all the power divergent terms, but it carefully hides itself in a strange place in the gauge theory. And we'll talk more about this later. It's not so important if you're working to order alpha s, but if you start working to order alpha squared or higher, then, or if you start going to higher orders in perturbation theory, then this could come in and be important. And it does come in QCD at fairly low orders. At order alpha squared can cause numerical effects if you ignore this. And there are ways of taking it into account without losing the nice things here. So we'll talk about that later on. And then there's a final thing. We should have 3 good points. We should have 3 bad points. The final thing we'll deal with right now, and that is the fact that MSbar does not satisfy something that's a theorem called the decoupling theorem. So what is the decoupling theorem? So this goes back to Appelquist and Carzone, and it says the following. So you're thinking about an effective field theory. You're thinking about deriving a low-energy effective field theory by integrating out some massive particle. And the decoupling theorem says that if the remaining low-energy theory is renormalizable, and we use a physical renormalization scheme, then you kind of get what you expect, that all the effects of the heavy particles turn up in couplings or effects that are suppressed. So this seems very physical from what we've described about what effective field theories do. So in that sense, I'm not going to try to prove it to you or anything, but there is this caveat that you need to use a physical renormalization scheme, of which MSbar is not one. So we decided that we liked MSbar, but then we found some problems. And this problem here, this last problem, we're going to deal with right away. So MSbar is not physical. And hence it doesn't satisfy this theorem. It's mass independent, and that is something that we like, but it also is causing exactly this problem. It's why it violates the coupling theorem. Because it's mass independent, it doesn't know enough about the mass to know that the effect of massive particles should always decouple. So in MSbar, what you have to do is you have to implement that decoupling by hand. And we've gotten actually so used to this logic that it's often even not mentioned that this is something that we're doing. So go over that a bit. So I'll just go over this in the context of a particular example, which is the most common example, which is QCD with massive particles. in MSbar. And I'll show you how it works. So QCD has a beta function of the renormalized coupling, mu d by d mu of g of mu. And just to establish some notation, I'm going to remind you of some facts that you've seen before. So this is the beta function at lowest order. I'll call this factor that depends on the group that you're dealing with and how many light fermions you have. I'll call it B0. And this is less than 0, and this is only the first order term in a series, but it'll be enough for our discussion right now. So there's g to the 5th terms, etc. That's the beta function for g. We can also think about using, since g likes to come squared, we can switch to alpha. QCD is asymptotically free. When we solve this equation for alpha, it looks as follows. And the coupling constant decreases as you go to higher energy. So if this is alpha at MB, and this is alpha at MW, alpha at MW is less than alpha at MB. Okay, this is the lowest order solution. So just a little bit more in the way of setting the stage. You can also associate to this solution here an intrinsic mass scale. Dimensional transmutation. If you form the combination mu exponential of minus 2 pi over beta naught, b naught, alpha of mu, and you use this equation over here, then what you'll find is that this combination is also equal to mu naught, same thing, alpha of mu naught. So it's independent of what choice of scale you use, mu or mu naught. Therefore, you define it to be a constant, and that constant is called lambda QCD. Once you do that, you can also just take this equation and write it rewrite that solution like this. So it's another way of specifying a boundary condition, if you like, for the differential equation. One way is to pick a value of the coupling somewhere. Another way is to fix this constant. So this guy's independent of mu, as I said, and it's the scale where QCD becomes non-perturbative. And the reason I have to mention this is because we're going to be talking about anomalous dimensions, and I have to tell you when the things that I write down are valid, and it's all going to be valid as long as we're not near this scale, because if we're near this scale, the coupling gets too large for us to do the perturbation theory that we're doing when we're calculating anomalous dimensions. So you can ask the question, what does this thing depend on? And if we look at the right-hand side here, we can already see some things it depends on, because it depends on B0. And if we look back at what B0 is, B0 depended on the fact that we were in SU3 if it's QCD. It also depended on the number of light flavors. So this scale that you fix here, well, it depends on the order of the loop expansion. We wrote down a formula that was valid at first order, but we could extend that formula to higher orders as well. And the formula would change and the value would change if we went to higher orders. Depends on the number of light flavors. And it actually also starts to depend on the scheme, but only at 2 loops. So it'll depend on MSbar versus MS, for example, but only beyond 2 loops. Now, the issue with this is that a priori, nothing tells us whether if you have a top quark or an up quark or a bottom quark. In MSbar, nothing a priori tells us what to do with these formulas, what to include in the B0. Just seems like we should include everything that exists, all the known light fermions that couple to the gauge field. Well, there might be some we don't know about. Should we include those too? MSbar, with the logic we've presented so far, doesn't tell us what to include there in that NF. So let me phrase it this way. That the top quark and the up quark, which have very different masses, both contribute to B0. And it seems like they do that for any mu. Even if I'm at a very low energy scale and the top is very heavy, MSbar is not smart enough to decouple the top quark. If you were to work in a physical scheme, then this decoupling theorem guarantees that actually that the top quark would decouple, and it would drop out of the beta function in that scheme. But in this MSbar scheme, it doesn't happen. So the solution to this is to build back in the thing that happened in the physical schemes into our MSbar scheme. And we do that by implementing the decoupling by hand. And we just say that when we get to a mass threshold, we're going to integrate out the heavy fermion in this case. So at some scale of order the mass of that fermion, we're going to integrate out the heavy fermion. And that's an example of doing matching, actually. You're moving from one theory to another because you're changing the field content. You're removing some fields, and that's an example of doing matching. So what this means is that we'll define different B0s depending on what scale we're at. So NF would be 6 if we're at scales above the top quark. But then we drop NF down to 5 once we're below the top quark mass, etc. So it's a discrete jump in what the B0 is. So in some sense, what that means is that this kind of matching is forced upon you in order to preserve physics in MSbar. If you were to do some other scheme, like a physical scheme, it's not to say that you couldn't take the same logic. You could do matching to integrate out heavy particles in those schemes as well. And in fact, sometimes people have. But in MSbar, it's really forced upon you. There's no way out, because you otherwise wouldn't get the physics right. So you've got to be careful. If you gain something, sometimes you lose something. And if it's physics that you're losing, you have to build it back in. OK, so how do we actually do this matching? Well, we use what are called matching conditions. So what is a matching condition? at some scale, which I'll call mu m, that could be equal to m, but it could also be equal to twice m or half m, some scale that's of order m, we're going to demand something about the theory above and below. And that is that S matrix elements in the two theories are going to agree. Of course, we should be careful to make sure that we work within the realm of things that we can calculate in the low energy theory. So we should consider only S matrix elements with light external particles. If we're getting rid of the heavy ones, we don't want them on the external lines. So the basic idea is that we set up matching conditions, which are conditions that say that S matrix elements should agree between theories 1 and 2, what we called theories 1 and 2 last time. So if we do that for QCD, the example we've been talking about, and we do it at lowest order, then the conditions are actually very easy. So here's the picture. Let's imagine that the top quark is here. The bottom quark is here. My picture is not to scale. Charm quark, etc. Then what we do when we want to say that the theory above and below, that threshold is the same, if we just match QCD above and below, it just is a continuity condition on alpha. So let me write it down at this scale. So here we would have alpha 6. Alpha depends on the number of flavors. Here we'd have alpha 5, a different definition of the coupling, a different number of active flavors, a different value of B0. And what these arrows are representing is kind of our normalization group evolution, which I'll just call running. And then what the lines are representing is doing some matching. So every time we reach a threshold, we do a matching, we switch the field content, and we get a new effective field theory with a new coupling constant. So the coupling just depends on what theory content we have. And the matching condition is, say at this B quark scale, that alpha S at 5, at some scale that's of order MB, is equal to alpha S at 4. That's the leading order matching condition here. And similarly, same condition at all scales. And this mu B, just to be clear, is something that's of order MB, could be equal to MB, could be equal to MB over 2, could be twice MB, and sometimes people use these different choices to get uncertainties. Okay, so it seems fairly straightforward, just continuity of the coupling. But that has some caveats, but go ahead and ask your question.
Yeah, so how do you know that that's the physical observable that you care about?
So
what if I was trying to measure the derivative of confidence?
So this is the, yeah, so if you're going, so you have to think about it as not the derivative of alpha S, but you have to think about it as an S matrix element, something 2 to 2 scattering, right? If you do 2 to 2 scattering, then it's just going to be proportional to alpha mu. But the mu dependence in your leading order prediction is not really fixed. You need to go to higher order to do that. So if you're just ensuring continuity at leading order of S matrix elements, then this is all you need. And if you want to construct something that's like a derivative of alpha, you have to think of the derivatives of the S matrix. But you can't take derivatives of mu because that's a higher order question. So this is all you need at leading order.
Okay, so maybe my derivative example is bad, but did you necessarily know that alpha S is the only?
So you, in general, right?
But I don't necessarily know that.
Yeah, no. In general, you have to. this is like one particular example. In general, you have to ensure continuity of all S matrix elements. And that will, in this case, will give you conditions also on what's happening with masses and stuff. So that it's all the parameters of the theory. There should be conditions for all of them.
I guess these words seem more complicated than just like asking for continuity of some, differential equation.
Yeah.
Does it ever boil down to anything? Do you ever have to do anything more complicated than just like?
I'm just about so
change the beta function and post continuity and.
It's not complicated. Just continuity of S matrix elements, but you have to just know that it's S matrix elements and not the Lagrangian, because those are two different things. So let me give you an example why it's not the Lagrangian. So this kind of thing seems simple, right? Just says, well, the Lagrangian's continuous, the alpha, the G that appears in the Lagrangian is continuous, but that's not true once you go to higher orders. Okay, that's only a leading order statement. If I write down the analog of this condition at higher orders, it looks as follows. So the coupling is actually not continuous in MSbar at higher orders. So demanding continuity of the S matrix elements does not lead to continuity of the coupling, and the matching condition at some scale looks like this. So the words are carefully crafted to be correct. And they sound a little more complicated than they need to be because I want them to be correct even if I were to do matching at higher orders in perturbation theory. And it's really at this alpha squared level that you start to see things that are more interesting. Okay, so now we've gone 2 orders beyond what I just told you before. So continuity at lowest order. At the next order, you can retain continuity as long as you pick the particular point where mu b is equal to mb. And then this log would go away, and you'd still have continuity. But even that doesn't work out once you go to one higher order. There's this constant. You could get rid of the logs by picking a scale choice, but there's no scale choice, which will make it continuous once you get to alpha squared in this matching condition. So this is the condition that's necessary to ensure continuity of S matrix elements once you get to that level of perturbation theory. Okay, so that is why I said S matrix and not just continuity of couplings.
So this condition is just for 2x2 scattering, and then you get other conditions.
This is the only condition you need for all the S matrix. You can use different S matrix elements, and they'll lead to the same condition. So it comes from ensuring that I calculate S matrix elements, say 2-to-2 scattering, in the theory with 5 flavors and 4 flavors, and I demand that up to 2 loops. So where would this guy here come from? This guy here would come from like the graph with an explicit B quark, which is in the theory with the B quark, but not in the theory without. Once you get to this level, then there's more complicated diagrams. Just think of generalizations of this. And they involve constants as well as logs. This guy just involves a log. And really what you're ensuring is that in the theory with the B quark, which is this 5-flavor theory, you get the same S matrix elements as in the theory with 4 flavors. Since the diagrams differ in those 2 theories, they're kind of the same at lowest order because you're just doing tree graphs, but once you have the B quark and it can go around in the loop, then they differ and the conditions become more complicated. Okay. So any other questions about that? Okay, so one other thing that we see from this is related to these logarithms. We also see from these conditions here that there's going to be no large logarithms as long as we pick the scale where we do this matching to be of order as MB. So you don't want to pick mu to be the gut scale or something. You want to pick it to be some scale. So mu is equal to mu b, which is of order MB. Because you don't want, for example, to make this log so large that it starts to overcome the coupling. You want this to really be a perturbative thing, so it makes sense to think about this, and then this is a correction, and that's another correction. Okay, so the general procedure is the same idea. So if I just kind of adopt a more general procedure for massive particles, adopt a more general notation. So this is with any operators and couplings, doesn't have to be gauge theory. And if we have a hierarchy of particles, let's say we have n of them, then we want to pass from an L1 to an L2, an L3, to an Ln. And we're doing the same type of thing we just did over there. So the steps are the following. Consider S matrix elements in theory 1. Do so at a scale, which I'll call mu1, that's of order m1, and match that onto, in the same way as assuring the continuity and using these matching conditions, match that onto L2. So this is the technical step by which I said that you could, in a top-down approach, take theory 1 and determine the parameters of theory 2. The matching conditions are determining the parameters. Alpha S4 is the parameter of theory 2 to alpha S5. This is theory 1. And we're just determining what this alpha S4 should be, and this is the condition that relates them. So after you do that step, if you want to go through this picture here, or the analog of that picture for this case over here, then you need to compute the beta functions in anomalous dimensions in this theory. So it's the theory that doesn't have particle 1. And then you evolve / run the couplings down, which just means using the evolution equation for the couplings, whatever they may be. So we had the evolution equation for alpha S a minute ago on the board, and I would just use that to go from a scale of order MB down to a scale of order MC. And then I repeat. And this is the general kind of paradigm of matching and running that you hear about in effective theory all the time. So we just keep going. And at the end of the day, we're going to stop somewhere. And the place we're going to stop is the place we want to do low energy physics. So let's say we stop at the nth level, since that's the last level I wrote. So if you're interested in dynamics at that scale, that's where you stop. And that's where you compute your final matrix elements. So everything up until that stage is just to determine the theory, Ln. And what are the values of the coupling in that theory, determined from knowing information at the high scale. Knowing information in theory 1, how do I propagate that knowledge all the way down to low energies consistently without losing information I need? And then once I'm at the lowest scale, I just do my computations of observables. Okay. Yeah. Sure.
You mentioned at the scale where the particle sits there. I'm still a little bit confused because if we are in the full theory, then say to scattering at
Yeah.
that mass scale,
Yeah.
isn't there any like a severe say resonance effect, and then you want to match that to a theory without the particle? I thought we should match.
So
at
there's
scale.
no resonance effect, and the reason is because the momentum on the external lines that you're taking, you're thinking of it as small, right? The scale is chosen to be the mass of the particle, the cutoff, mu,
Oh.
the soft cutoff, but not the momentum
No,
of the
it makes-
particles.
Oh, yeah.
Good question. Any other questions?